My name is Andrei Garko, and in this presentation I'll be talking about advanced data structures and algorithms for data-intensive applications. Such things are also called probabilistic, and we will use PDSA as the acronym, where P stands for probabilistic and DSA for data structures and algorithms. A few words about myself. I work as a senior software engineer at Ferretgo GmbH, the leading community moderation, automation and analytics company in Germany. Beside that, I hold PhD in mathematical modeling and numerical methods, and I am also the author of the book Probabilistic Data Structures and Algorithms for Big Data Applications, which is actually the reason why I'm here today. Follow me at Twitter or visit my page at garkov.com. Let's start. Nowadays we produce an enormous amount of data. Every single second we generate millions log entries. An unbelievable number of IoT devices send their information to servers. Terabytes of data are recorded by various machines, planes, and so on. No doubt we need all those data because it creates new opportunity to learn and opens new horizons for different businesses. However, this also implies lots of technical challenges, what we want to talk about today. Many of these problems can be solved with parallel computation, included usage of the MapReduce paradigm and such popular frameworks for distributed processing as Apache Hadoop, Apache Spark, Apache Flink, Apache Storm, and many others. But unfortunately, at some point, the amount of data, or its frequency, or variety, or altogether, it rises so high that we cannot scale up our systems anymore, regardless the amount of money and resources we have. Thus, we have to agree to lose some of data in order to be able to continue our processing, so to continue learning. There are two main approaches in this case to go. This is sampling and hashing. With sampling, we process some subset of elements instead of the full data set, and we discard the rest. It's still good, and usually consider it as the first approach to try. Since we still can use the existing setup, we can use the same algorithms. However, we need really carefully choose the subset of data we want to process, because afterwards we won't interpolate all results that we obtain of that subset to all data. Another approach is hashing, which allows to process all elements without exclusion, but it implies some information loss. And also there is some probability of error due to the possible hash collisions or due to the different algorithms. This approach is very, very, very powerful, but in contrast to sampling, it requires advanced algorithms. And in most cases, afterwards, you will get or you have to approximate results. And as you might guess already, PDSA use a hashing approach. And it also based on very smart ideas and observations, which allows us to provide really, really close and correct answers with really, really, really limited resources. While it may sound a little bit theoretical, you may use probabilistic data structures already and every day without noticing that. I will give you a few examples during the presentation, but first look at Apache Spark. I hope everybody knows this very nice and powerful framework. Thus, if you want to estimate frequencies of elements in a data frame using a Spark SQL, you can use a count means sketch function that actually a probabilistic data structure. Another example is the approximate count distinct function, but also a probabilistic data structure and uses hyperlog++ algorithm to approximately count unique elements in a column. Actually, almost any modern software that works with data uses some probabilistic data structures. You can find them in Google Big Data and Amazon Redshift, Redis, Elasticsearch, Cassandra, and many others. But before going into particular use case, let's look which problems on big data can be addressed with probabilistic data structures and algorithms. I guess everyone heard about volume, velocity, and verity, the 3 V's of big data. That actually highlights the main challenges we face in the data processing. On the diagram, you see the relation, and let's start explaining it. So many people associate big data just with the high volume. So let's first look on that branch. The first problem in the high volume, what we can address with PDSA, is the membership querying. This is a task to check if an element exists in a dataset or not. PDSA avoids storing all elements. It allows us not to store even hashes of these elements. These are very nice and very, let's say, very known probabilistic data structures. For instance, most popular, and maybe you already heard about, this is a Bloom filter. Also, there are Cuckoo filter and quotient filter, which can solve such problem very efficient. Another important problem is counting. What can be solved also with probabilistic data structures and probabilistic counters such as log-log, hyperlog-log, and many others. The second characteristic of big data is velocity. This is the speed of how data arrive in. Nowadays, it enormously increased thanks to the rise of IoT. This is a very interesting challenge as well, and there are many traditional approaches exist in such stream processing. But if we are talking about probabilistic data structures and algorithms, we can use them to estimate frequencies and quartiles in data stream very efficient. I already mentioned count means sketch, which is used in Spark SQL. And also there is a count sketch, for instance, as an alternative to that algorithm. For rank estimation, I want to highlight T-Digest that was developed by Ted Dunning from MapR. And finally, we have verity, the number of different kinds of data what has to be mapped. It can be addressed with locality-sensitive hashing, that is implemented as a min hash and sim hash algorithms in data structures, and used in Google for personalization and recommendations. And today we are going to talk about counting, but if you're interested in other mentioned problems, so feel free to read the book. The link will be shown at the end, and then contact me if you still have any questions. So counting. This is the task to find the number of unique elements in a dataset where duplicates are present. Of course, we're interested in cases when the number of elements is huge and their size is large. And let's start with a traditional approach to solve such a task. First of all, what we do usually, we can allocate an array where we store all unique elements seen thus far. Then, since we don't want duplicates to be saved, of course, we can use the sort to check if the element is in the array already. Additionally, to speed up this process a little bit, we may sort the array additionally, of course. And as soon as we want to know the number of unique elements, it's easy. We just simply count elements in this array, and that would be our number of elements. And this works. This works actually quite good when we have not so many elements and they are relatively small in size. But this approach requires linear memory. That means we have to store all these elements, and as soon as we have more elements, we have to store more of them in the array. And if elements are large and its number increases drastically, such an array grows very fast as well until it has to be stored on the disk. And disk is very slow. Once this happened, we may hit another problem, because the probing algorithm which we designed, which involves sort and search, has a quasi-linear or n logarithm n time complexity, and it could be notably slow in this case. Let's look at a simple example. According to publicly available statistics, Amazon, eBay, and Walmart in 2017 had about 144 million unique visitors a month. If we associate every visitor with its IP address, which we will need 2.3 gigabyte just to store this list using 128-bit IPv6 addresses. But if we identify users not just with IP addresses, but with some bigger session IDs, or we want to include some other parameters, we will need much more memory. But what if we can accept some error in counting, and then we can employ PDSA and count all these visitors with just 12 kilobytes of memory? But actually, can we imagine a situation when we can accept errors in such numbers? Let's look at Twitter. Katy Perry has the most followed account these days. She has 107,280. But wait, do we really care about the exact number? Thus, this is a perfect case to count with probabilistic data structures and algorithms. So, how we can compute approximate counts? Actually, approach is very straightforward. As I already have mentioned, we just need hashing, which out of the box provide deduplication. So we always hash the same elements into the same values. Then we can hash every element and represent the hash value as a binary number in LSB0 format. Means least significant bit goes at 0 position. Then the number of zeros at the beginning we will call rank. For example, at the slide you can see there is number number 42, which is a result of applying some hash function to element hello. And its rank will be 1, since we have exactly 1 0 before the first one appears. It's in bold at the slide. And now the counting idea becomes very simple. We process all elements and store somewhere all seen ranks. As soon as you can see, this is already an improvement, by the way, to the traditional approach, because we don't need to store elements, we don't need to store hashes, we just need to store some small integer rank. Interesting, but there is a relation between the distribution of such ranks and the number of elements we process. This is actually the theory behind this type of probabilistic counter. And as you can see, the more elements we process, the closer we are to the stable state where what can be forecasted by the theory. Maybe it sounds too complex to you, but look at the example with coins. Theoretically, we know what the expected distribution is 50-50 for tails and heads. But in practice, if you can take and try to toss a coin as many times as you can, but you will see there is always some error. But the more trials you have done, the closer this error to the zero. This is kind of similar theory behind the probabilistic counter as well. So technically, we can store all such observed ranks in a simple binary count. So for instance, we see the rank 2 and then we just set that the corresponding bit to 1 in such a binary count. Theoretically, we can estimate the likelihood of every bit to be set. So you can see it at the slide and can notice that the growing number of unique elements, the beginning of such a counter, almost certainly has all ones, because low ranks appear more often, and while ending has almost certainly zeros, because high ranks appear rarely. And only the middle or center part is about 50-50, which depends on the number of unique elements. And this dependency we want to employ into the algorithm. Thus, we just identify that middle part as the leftmost zero. We denote it as R, and use it to compute the approximate count of unique elements. It's not a complex formula. And so we just find an indicator of logarithm n, and then we can revert this formula and find the n. And in this case, it's quite easy. So, for instance, on the slide, if you look on the formula from our counter, we see what the r equals actually to 4. That means 2.2 power 4 is 16, and then the n would be 16 divided by some constant, which is 0.77, and at the end, the number of unique elements, which is 21, which is defined by the counter we see at the slide. And as you can see, this approach is very simple and it requires only a single binary counter instead of array of all unique elements, as we will go with a traditional approach. However, we can expect quite a big error, by the way, because it's not a very good idea to estimate some random values with only one estimator. Again, if you think about the coin, which results you would trust more? The one obtained by a single person with a single coin, or an average from many different persons with different coins? Thus, we need some improvement to this algorithm, and this improvement actually was done in the hyperlog algorithm, which was proposed in 2004. This algorithm uses a single 32-bit hash function, and it simulates many counters by taking part of the hash value for addressing. We call such part or such bits as a precision, and then it uses the rest of the hash value for rank evaluation. Thus, if we have p bits allocated for addressing, we can have 2 power 2 in power p counters. But this is not the only difference from the probabilistic counter. Instead of remembering every rank, what we have seen during the processing the elements, we can store only the maximal rank which we observed by the counter. So every counter we store a maximal rank what was absorbed by a particular counter. In this way, we need only some small bytes, usually 4 bytes for each counter, meaning the overall memory is fixed and quite small. With such setup, we can estimate the number of unique elements with a bit more complex, but it's still a readable formula, where you can see it at the slide, whereas the alpha is some predefined value which is related on the number of bits what we use for addressing or precision. Let's look how hyperlog works at the practice. Now you will see a demonstration where we'll use 64 counters. So this is a hyperlog data structure with 6 addressing bits, or precision equals to 6. And it requires only 256 bytes of memory. And from the theory, we know what the expected standard error will be, about 13%. So as you can see, at the beginning, all counters are 0. And now we will start indexing city name from different counters and see how the hyperlog data structure changes. As already mentioned, we save maximal observed ranks into the counter. So every element selects only one counter based on its addressing bits. And then we update this counter. You can see this jumping green square. But it happens only if the rank of the current element is higher than the already stored value, because we are interested only in the maximal rank for each counter. At the bottom, you can see the relative error between approximated and the actual number of unique elements. And at the right, I output the currently processing element and the current error. Okay. So we indexed 998 elements, and as you can see, the approximated value is 1083. We have some error of 9%, which is less than theoretically expected, and this is good. But is it acceptable or not? It's a good question, and usually it depends, and it depends on your application and your use case. But please note what in this demonstration we use quite a small data structure. It's only 64 counter. This is mostly for demonstration purposes. But in practice you will take more counters, what will guarantee even smaller error, but of course you will pay with some additional memory to store those counters. And actually, all probabilistic data structures and algorithms imply some trade-offs, what you have to be aware of. In the case of hyperlog, we clearly can achieve better accuracy by allocating more counters, which require, of course, more memory, and vice versa. At left, at the diagram, you can see how the standard error in percents is decreasing with bigger precision values. So the more a number of addressing bits we use, so the more counters we use. While the right charts show how this at the same time memory consumption is increasing. As already said, in our demonstration we use only 6 bits for addressing, so only 64 counters, and it was rather memory optimized than the accuracy focused, what we also already mentioned in the result before. But please note what in hyperlog we have a natural limit on the number of counters what we can use, because we cannot take more than half of the 32-bit hash value for addressing, because otherwise we will hit a problem with the hash collision, since we will since we always use the rest of the hash value to compute the rank, and as soon as it becomes small, it becomes too ambiguous and probably will hit some collisions, and our result will be less precise than it expected in theory. So enough theory for today. Let's look at how hyperlog actually used in practice. So let's look at Redis. This is a well-known in-memory database. It uses hyperlog log of 12 kilobyte to count unique elements in a set. There are commands pfadd and pfcount, where pf stands for Philippe Flageolet. This is the author of log and hyperlog algorithms. And then with pfadd, you can just create hyperlog log if it's not yet created and index elements and new elements into it. And then as soon as you need to compute the approximate number of unique elements, you simply run pfcount and get the result. It is also easy to use it in Python directly. In this example, I use the Python library PDSA. This is a library what I wrote. The link you can find at the end. But there are many other implementations in different languages, so you can import and try. At the slide, we create a hyperlog log using 10 addressing bits, meaning we use 1024 counters. They require 4 kilobytes of memory, and it's simple as the Redis example. So we simply read from the file and index all values we take from it into our data structure, and as soon as we need the number of unique elements, we just do dot count and get the approximate cardinality. If you want to implement hyperlog log yourself, it's easy too. But I would really suggest using Cython. If you're not yet familiar with Cython, this is a Python compiler that allows to easily create C extensions and better control memory allocation. Which is really important in probabilistic data structures then, because this is the reason why you use them usually. The hyperlog log class can look as at the slide. So here we define counter as an array of unsigned long integers, which are 4-byte integers. The computation of addressing value and the hash value can be done just by using a standard divmod function. And then the actual estimation of the cardinality is very simple. We collect all stored ranks from all counters and apply harmonic mean on them. Additionally, as you can see, there are some corrections for very small and very big cardinalities. We need them, and because algorithm has some nonlinear biases, and using these corrections can actually improves the algorithm. However, this is not the only improvement we can use. And the biggest improvement of hyperlog log has been done by Google, and it's known as hyperlog log++. The obvious difference, it supports 64-bit hash functions, while hyperlog log supports only 32-bit hash function. That means hyperlog log++ allows to have more counters and thus count to bigger values. Another key feature is a better correction, which is done by some sort of machine learning technique on top of that, using the pre-calculated by Google values, which allows to better tune the algorithm for different distributions. This modification is quite popular. For instance, Elasticsearch uses it in their cardinality aggregation, and as we already saw, Spark SQL uses it to compute approximate count of distinct elements. That's it for today. If you want to learn more about counting and probabilistic data structures and algorithms, take a look at the first 3 sources, what gives you the direction. More probabilistic data structures you can find in my book. Visit pdsa.kakov.com for details. Also, you are very welcome to use and participate in the PDSA Python library link you can see on the slide. And also these slides and the video will be available to you afterwards. So thank you very much. That's it for today. If you have any questions, I would be happy to answer. Thank you.